Before we go over rate equations, just a reminder to brush up on your math, so you know how to work with powers, etc. So just pause it there and go over that and review that if you need to. Okay, so the rate equation, so if you hear rate expression, rate law, they're all the same thing. Okay, so it could be a little bit confusing. So it basically tells you what the effect of all the different factors are on the rate of reaction. Now, this includes catalysts. And so if there's a catalyst, that B could very well just be some catalyst. So if you double B, double A, you're going to double the rate. If you double B, it's 2 to the power 4, it quadruples it. So you can have powers to the 3 and the 4. They're a little bit rarer, but it's most commonly to see the first and second orders. Okay, now another key thing is you can only find it by actually doing experiments. You can't predict it because we don't really know the complexity of these experiments. Now, again, if you go back to that thiosulfate reaction, that's helpful because you can see that the orders can actually be, they don't have to be whole numbers. They can be like fractions. So that with respect to, I don't know what it was, I think it was HCl. And then to get even nastier, you can actually, if you change the concentration of the HCl, it can actually change the rate orders of the other individual parts as well. That's how crazy all this stuff is. Okay, so we don't know what's going on. But we're experimentally, we can determine what the rules are. Okay, what the rate equation is, and hopefully it's not a crazy one where it's actually a lot more complicated than what we're presenting to you. Okay, so the rate, of course, is change in products or reactants, decreasing reactants over time or increasing products over time. So, of course, there's the concentration, so moles per litre per second. And I think that's it. We can get into a little bit more detail. So, order of reaction, so this is terminology. So the order of reaction, so that's to first order. So increase that, increases the rate, double that, double the rate. Second order, double that, it quadruples the rate. And then that's just the order with respect to each component that does increase the rate. And then overall, you add up all the little pieces. And so for this particular one, it's 1 and 2. So 1 plus 2 is 3. So the overall order is the third order. Now, the units are a little confusing too. So in order for the rate to always be this thing here, moles per litre per second, when you keep on adding more and more moles per litre, moles, decimeters to the -3, what you have to do is you have to keep dividing the K by that value so that the final units is moles per litre per second. And so if you have like 2 of these, you're going to have to keep dividing by moles per litre. So for the first one here, K it has, so there's no order, then the rate's fine. But once you start adding the first order here, this one has moles per litre, decimeters -3. That's not a rate. So you need this unit to have the seconds. Now, if you have a second order, what you're going to have is you're going to have moles per litre and then times moles per litre. And so K is, what's K missing? How are we going to get K to be this? We need to divide by moles per litre, and we need to have an S -1. Okay, so in order for that to happen, you've got the S -1, and then you're going to have this as this here, a divide by. So you're going to have to, this is a positive and this is a negative. Okay, so I don't know if that makes, how much sense that makes to you, but basically we're getting, the K always has these weird units so that the final R always equals moles per litre per second. And that, why do we keep dividing by moles per litre? Because we keep on adding moles per litre when we add another one to it. Okay, so I hope that makes sense. If it doesn't, just do this. Divide the rate by as many concentrations as appear in the rate equation. Okay, if you don't understand it, just do that. Okay, now This is, you can read through this in your own time and just pause it. So this is just a review. How do you get rates? You do the gradient. I covered that in rate of reactions. And that's just going into details of a specific example. Just pause it and read it if you need to. Okay, now there's two ways to work out what order it is. There's concentration versus time, and there's rate versus concentration. Now, I generally don't know too much about this one because I don't do it, because you're basically just doing one reaction, and then if you go down to here, what you're doing is you're doing one reaction and you're taking the instantaneous rate at different points. So for this one, it's asked to do at these points here. So you take the tangent to the curve. So at a concentration of 1, you took an instantaneous rate. So because that's not an initial rate, you're not controlling temperature. And so there's a bit of a flaw in this, so I don't really do it. But you need to be aware of it, because you could see some people might do it this way and you could get questions, and you have to have a very careful look at your graph to make sure you're looking at the right thing. So make sure you're looking at the first one's concentration versus time. The second one is rate of reaction versus concentration. So if you're doing it this way, it's a straight line, it's zero order, there's no effect of changing the concentration on the rate of reaction. If it's curved, like a half-life, then it's first order. So halving the concentration halves the time. And anything higher is second order. Now, their suggestion for you to work with that, I don't do it because it's not controlling your variables, is to change the plot on your graph to double. I guess you do that in Excel to save time, and then keep on going until it's a straight line. And so if it's a straight line, if you've plotted rate versus double concentration, then you get, and it's a straight line, then you got second order. So just be aware of it. Don't do it that way, because I said it's not a good method. So you could lose a mark for method there. And so this is the one that I do because what I do is this here. So you do a different experiment for each concentration, and so you get lots and lots of these, and then you'll get an initial rate for each one. So you've controlled temperature and concentration properly, and then so you'll get like different rates, and then you'll draw a graph that does concentration versus rate of reaction. And then if it's a straight line, it's a straight line here across, it's first order. And then you'll have these ones here. Where are they? Then you'll have, zero order if there's no change. Oops. So it doesn't matter what you do to concentration, reaction rate doesn't change. And then this will be like first order if it's a straight line. And then once you get to these curves, what you then do is you tell Excel to plot an exponential line. So y equals mx and to the power of what. And the computer will give you the line of best fit and tell you if that's a 1 or a 2 or a 3. And as I said before, it can be a fraction. Okay? And then you can compare that to published results. So that's the best way to do it. And that's why I don't really, besides being aware of one in case I get a question or I have to see something, I don't really care too much about the first one. Okay? And so have we covered everything there? Okay, so that's all covered there. We just do a practice question, and funny enough, the practice question is done properly, and it's asking for everything that we just covered: orders, individual orders, overall orders, rate equation, value of K, and units. Okay, so that's the data that we have. So you can do all of this with just 3 reactions. Okay, so first of all, orders with A to B. So you, with respect to A, you've got to make sure the B stays the same, so you can compare A. And then when you're doing B, you have to keep A the same, so you can compare B. Okay, so we're doing, with respect to B, A is, B is kept constant. So when you keep constant and you triple A, so it's gone 0.5 gone 3 times higher, all right, then you get 2, 4, 6. Then you get tripling of the rate as well. Okay, so that's first order, doubles, triples. So we know that the with respect to A, the order is 1, not 0, not 2. So if we have a look at B, when you keep A constant here and you double B, it goes from 2 to 8. Okay, so A is kept constant, B doubles, the weight quadruples, 2 to 4, therefore the rate to B squared. So it goes from 2 to 8 when you double it. So that's to the power of 2. So R equals B to the power of 2. All right, with respect. So that's the order with respect to B when A is kept constant. Hope that makes sense. Okay, and so the overall is you add the 1 here and you add the 2 here, and that adds up to 3. So overall order of reaction. So just finishing off now, the rate equation, then we just put the whole thing together. And then we just grab any one of these lines. So I think I've grabbed this line here, and I need to sub all those numbers in to get the actual K value. And so I sub those numbers in, I have to rearrange this, throw this down to the bottom. Sub the numbers in, I get 4. Now, because there's 3 concentrations, the units for that is going to have to be divided by moles per litre 3 times. All right, so we're going to have the seconds minus 1, and then so if we can see here, concentration. So the rate needs to look like this. All right, but I've added 3 of these. So that's moles to the 3 to the negative 9. I cancel that out. So this is where the powers come in. So that goes to a 6, and that goes to a 2. That's where your powers revision come in. And then we sort of link the negatives together at the end there. So now it gets swapped around, which is kind of annoying, and that goes to a positive. So it's sort of, yeah, it looks pretty nasty. And so then the final thing is you just write the final thing out. So the K equals 4 decimeters to the power of 6, moles to the negative 2, seconds to the negative 1. And you've done the whole lot.